Board, China has just shown the world a new method for turning seawater into drinkable fresh water using nothing but sunlight, no grid electricity required. A research team built an outdoor rig that occupies less than a single square meter. Under natural sunlight, this prototype reportedly delivered just over 20 liters of clean water per day. That is, board sufficient to cover the basic daily drinking needs of roughly 10 people. The collected liquid met international potable water standards, and the scientists went further, using it to irrigate a small test plot through complete crop growing cycles. But the truly significant part is not simply that sunshine can evaporate seawater. Humanity figured that out thousands of years ago. The genuine breakthrough is the material packed inside the device. Chinese researchers engineered a three-dimensional photothermal architecture designed to soak up sunlight, concentrate thermal energy right at the water's surface, supercharge evaporation, and operate without any connection to the electrical grid. In laboratory tests, this material hit an evaporation rate of 38.14 kilograms of water per square meter every hour. That was more than 8 times the performance of the team's earlier flat design. The system also absorbed over 90% of incoming sunlight and reportedly slashed the energy required for evaporation by nearly 46%. If this technology can be scaled reliably, it could deliver drinking water to islands, coastal villages, farms, and disaster zones where massive desalination plants are far too expensive or where electricity supply is unreliable. But can a compact solar prototype genuinely compete with industrial-scale desalination? Or is this simply another dazzling laboratory result that becomes brutally difficult once engineers attempt to build it at useful scale? To answer that, we need to understand why converting seawater into drinking water remains so staggeringly expensive. Why desalination guzzles so much energy? The ocean contains a virtually infinite supply of water. But seawater also carries salt, minerals, microorganisms, and other contaminants that humans cannot safely consume in large volumes. Stripping those substances out demands energy. The most widespread modern technique is reverse osmosis. A desalination facility uses powerful pumps to blast seawater through membranes containing extraordinarily tiny pores. Water molecules slip through, while the vast majority of dissolved salts get blocked. The process functions well and operates in large installations across the globe, but it demands intense pressure. Generating that pressure consumes enormous amounts of electricity, and the plant also requires pre-treatment hardware, filters, pumps, membranes, monitoring electronics, and constant maintenance. Another method leans on heat. Seawater gets evaporated, leaving the salt behind, and the water vapor is then condensed back into clean liquid. This mimics the natural water cycle. The sun evaporates ocean water, clouds assemble, and fresh water returns as rainfall. Industrial thermal desalination can generate huge volumes of water, but heating that much seawater swallows staggering quantities of energy. That is precisely why researchers are so interested in solar evaporation. Instead of warming an entire massive tank of water, a photothermal material captures sunlight and focuses the thermal energy only where evaporation actually happens. The objective is to generate water vapor while wasting as little energy as physically possible. How the Chinese material actually works. The new system deploys a three-dimensional photothermal structure. Photothermal simply means the substance converts light into heat. A flat, dark surface can already accomplish this. Leave a black object under direct sunlight and it gets hot because it absorbs more light than a reflective surface. But a high-performance solar evaporator must achieve far more. It must capture a broad spectrum of sunlight. It must funnel heat into a razor-thin layer of water rather than warming the entire reservoir. It must continuously draw fresh seawater toward the evaporation surface, it must permit water vapor to escape freely, and it must prevent salt from board clogging the entire structure. The Chinese team developed a three-dimensional design boasting a much larger active surface than a conventional flat absorber. That extra surface area enables more water to interact with the heated material simultaneously. The structure also helps trap thermal energy near the evaporation zone, instead of allowing board heat to dissipate into the bulk seawater below. More of the captured sunlight gets deployed directly to convert liquid water into vapor. The researchers reported solar absorption reaching up to 90.2%. They also stated the design reduced the effective energy demanded for evaporation by 45.7%. This does not violate the laws of physics, board, or conjure energy from nowhere. Water molecules still require energy to break free from the liquid. The material simply alters how efficiently heat gets delivered and may also modify the local interaction between water molecules and internal surfaces. The outcome is dramatically faster evaporation from the same quantity of board. Sunlight. Board, the 38.14 kilograms result unpacked. The headline laboratory figure was 38.14 kilograms per square meter per hour, since 1 kilogram of water equals roughly 1 liter. That sounds like the device could pump out over 38 liters of drinking water every hour from a single square meter. But that interpretation would be deeply misleading. The board number describes the measured evaporation rate under tightly controlled test conditions. Evaporated water is not automatically collected drinking water. A complete system must capture that vapor, shuttle it toward a cooler surface, condense it into liquid, and store it without contamination. Every single step introduces losses. Laboratory. Board. Illumination may also differ dramatically from shifting outdoor sunlight. Clouds, wind, temperature, humidity, and the angle of the sun all hammer real-world output. That is precisely why the outdoor prototype carries far more weight than the laboratory. Board. The real outdoor prototype. The researchers assembled a system with an active area of roughly 0.75 square meters. It was tested outside using genuine natural sunlight rather than a controlled indoor lamp. The complete device generated 20.16 liters of fresh water in a single day. That sits far below what you would get by multiplying the peak board laboratory evaporation rate across 24 hours. But it represents a much more meaningful figure because it describes water actually harvested by a functioning outdoor system. 20 liters is not enough for the total daily water consumption of 10 people. Cooking, washing, sanitation, and agriculture demand vastly more, but it can cover board basic drinking needs that could prove critical in remote locations where fresh water currently must be transported by truck or boat. A small village could deploy several modules. A disaster relief team could roll out portable units where the power grid has collapsed. Coastal farms might use larger arrays to supplement irrigation water. The system board would still depend on weather and sunlight availability, but it could operate without the continuous electricity appetite of a conventional reverse osmosis. What no grid power genuinely means. The device is sometimes described as electricity-free. That wording demands context. The system does not function without energy. Its energy arrives from sunlight. The photothermal material soaks up solar radiation and transforms it into heat. The accurate claim is that the prototype can produce water without board being plugged into an external electrical grid. That distinction matters enormously. A reverse osmosis plant may require uninterrupted electricity for pumps. A solar evaporator can operate passively during daylight hours. However, a larger commercial system might still employ small pumps, sensors, fans, or automated controls. Electricity could also prove useful for moving seawater, gathering collected water, cleaning equipment, or operating at night. The central advantage is not that electricity becomes forbidden. It is that the primary energy-intensive step, evaporation itself, gets driven directly by the sun. The salt obstacle. Salt represents one of the biggest barriers confronting solar desalination. When water evaporates, dissolved salt stays behind. As evaporation proceeds, the water near the surface grows increasingly concentrated. Eventually, salt crystals can form directly on the photothermal material. Those crystals block sunlight, restrict water movement, and cripple performance. A laboratory device might perform brilliantly for several hours and then become far less effective after days of salt accumulation. Any practical solar evaporator needs a strategy to manage concentrated brine. Some designs permit salt to diffuse back into the larger seawater reservoir. Others employ bored channels that continuously flush water through the structure. Some devices get periodically rinsed, while others are engineered so that salt crystallizes in a separate location where it can be removed. Long-term durability will rank among the most critical tests for the Chinese system. The prototype must demonstrate that it can survive repeated board wetting, drying, heating, and salt exposure without losing performance. Coastal seawater also contains biological material and minerals that may foul surfaces over time. Producing water for one successful demonstration is entirely different from operating every single day for multiple years. The farming experiment. The researchers did not stop after measuring water in a container. They used the fresh water to irrigate a test plot covering approximately 5 square meters. The system reportedly sustained complete crop growing cycles. That experiment carries weight because agriculture is the planet's largest consumer of fresh water. Many water-stressed regions sit near oceans, but seawater cannot be applied directly to most crops. Salt accumulates in soil, damages root systems, and eventually renders farmland barren. A modular solar desalination system could supply small quantities of fresh water for greenhouses, seedlings, or high-value crops. It would not immediately replace the colossal irrigation networks serving rice, wheat, or corn. Those systems shift thousands or millions of liters, but it could prove valuable for remote islands, desert communities, or small coastal farms where every single liter of clean water is expensive. The cost projection. The researchers estimate that after roughly 2 years of operation, the cost of the produced water could dip below the price of commercial bottled water. That is a projection, not a confirmed market price. Bottled water also represents an easier benchmark to beat than municipal tap water. Bottled water includes packaging, transportation, storage, and retail profit margins. A large reverse osmosis plant may generate water at a far lower cost per liter than bottled water, especially when operated at enormous scale. The true economics will hinge on the cost of the photothermal material, the condenser, supporting structure, maintenance, cleaning, lifetime, and installation. If the device demands frequent replacement, the water will remain expensive. If it survives for years with minimal maintenance, the economics become dramatically stronger. Local conditions will also dictate viability. In a city with an established water network, the system may never compete with tap water. On an isolated island where bottled water arrives by boat, it could be far more attractive. Can it actually scale? Scaling is the central question hanging over this entire technology. A 0.75 square meter prototype can be carefully assembled and monitored by researchers. A commercial system may need hundreds or thousands of square meters. Every module must distribute seawater evenly. Vapor must be harvested efficiently. Condensation. Surfaces must remain cool enough to convert vapor back into liquid. Powerful winds, storms, dust, salt spray, and biological growth must not wreck the equipment. The system must also dispose of concentrated brine responsibly. Large desalination plants return salty waste to the ocean, where it can harm local ecosystems if not properly diluted. A solar system produces less water per unit, but a sprawling field of modules could still generate a significant waste stream. Manufacturing presents another hurdle. The photothermal structure must be cheap enough to produce in massive quantities. A material with dazzling laboratory performance may depend on complicated fabrication steps that render commercial production prohibitively expensive. Engineers will need to simplify the design without sacrificing the properties that generated the high evaporation. Where it could be deployed first. The technology is most likely to succeed initially in locations where water is precious and electricity is scarce. Small islands represent one obvious market. Many islands enjoy abundant sunlight and seawater, but depend on imported fuel or bottled water. Remote coastal villages could use modular units for drinking. Board and cooking disaster zones constitute another possibility. Earthquakes, floods, and storms can shred power lines and contaminate freshwater supplies. Portable solar desalination equipment could begin generating water without waiting for the electrical grid to be rebuilt. Military bases, research stations, ships, and offshore facilities may also board value systems that reduce dependence on transported water. Agriculture could become another market if the device gets combined with water storage and efficient drip irrigation, but the technology is unlikely to replace giant municipal desalination plants anytime soon. Cities need reliable water every hour of the day, regardless of weather. Board conditions. Large reverse osmosis facilities already produce hundreds of millions of liters daily. Solar evaporation will probably begin as a supplement rather than a wholesale. Board replacement. My take is that this represents a genuinely promising water technology, but the 20-liter outdoor result matters far more than the spectacular laboratory figure. The researchers have shown that the material can move beyond a tiny indoor sample and produce usable fresh water under natural sunlight. That constitutes a meaningful step. Board forward. The system could prove especially valuable where transporting water is expensive and grid electricity remains unavailable. But it is not yet proof that China has solved global water scarcity. The prototype remains small. Long-term salt resistance still demands demonstration. The manufacturing cost must fall substantially, and larger board systems must prove they can collect and condense vapor efficiently in real weather conditions. Still, the concept attacks one of desalination's biggest problems head-on. Instead of burning massive amounts of electricity to shove seawater through membranes or heat enormous tanks, the system deploys a carefully engineered material to place solar board thermal energy precisely where evaporation occurs. The ocean supplies the water, the sun supplies the energy. The material bridges the two. If China can convert that laboratory efficiency into durable, mass-produced equipment, the technology could hand remote communities a fresh source of drinking water without waiting for a power plant or a bored massive pipeline. So what do you think? Could sunlight-powered desalination become a practical solution for water-stressed coastal regions, or will scaling, salt accumulation, and maintenance keep it confined to small installations? Let me know your view in the comments, and subscribe to Empire of Tech for more sharp, grounded coverage of the board technologies, factories, and engineering decisions reshaping the global economy, because China has not erased the cost of desalination, but it may have discovered a way to replace a major chunk of that cost with nothing but board sunlight.